Okay, good morning, everyone. If you are in the East Coast, or good afternoon if you are in Europe. So today we have the pleasure to have Robin Cole, who's an expert in satellite imaging and deep learning. So a bit of Robin's background. He was trained as a physicist. He got a PhD from the University of Cambridge, University of Isaac Newton, I believe. And so he's based in the UK. So he's passionate about this topic. He has a website. I think has a YouTube channel. He has a podcast. So you can find him at satellite-image-deep-learning.com. You can just find him on LinkedIn or Google him. So he's on Discord, YouTube, on GitHub. So I noticed Robin because he had a very interesting, many interesting posts, and he's very up to date about satellite imaging. So I think that it'd be very good for us to have his perspective on the field, which is evolving very fast. Okay, so Robin will talk about for around half an hour, and then we have some Q&A. Robin will have to have some commitment after that, so we'll have to end after that. Okay, so the floor is yours, Robin.
Thank you so much for the introduction, Min. So I'm going to slightly repeat what you said on my first slide, introducing myself, but for people that are just joining, hopefully that will allow you to recap. So yes, I'm Robin. I'm based in the UK. I live in London, actually. And I recently started a new role as a senior software engineer at a Canadian company called Earth Daily Analytics. And we're going to be launching a constellation of satellites next year, which is going to capture very high quality imagery. Previously, I've worked in R&D. As Min mentioned, I've got an academic background. I did a PhD in a different area of physics, actually. And I've also worked in industrial R&D. For the last almost 10 years or so, I've been working in the space sector. Actually started off on the hardware side, working at a company in the UK that makes satellites. And I was working on optical engineering, essentially. But over time, I moved more into the software side. This is coming from a background of enjoying working with the Python programming language, which has become a mainstay of machine learning. As Min mentioned, I'm also very passionate about this topic, and I've created a website. The URL is there. You go into this website, you'll see that I publish regular newsletters, and actually a lot of the content from the newsletters I'm using in this presentation today. I've also got a YouTube channel, and that's growing quite nicely. That covers both technical topics, but also the people behind the work. And I've just got a screenshot of it down there. So the context, what's going on in the satellite imagery sector? Well, there's essentially an awful lot happening, driven for a couple of reasons, but one of the main drivers is the fact that launching satellites has gotten so much cheaper recently. SpaceX and others are making it increasingly cost-effective to put satellites into space. And you're seeing an abundance of new companies entering the Earth observation area. Many of these companies are startups. Many of them are putting up kind of very innovative satellites that can do new kind of capabilities, imaging in different parts of the spectrum, or with different kind of business plans revolving typically around creating large constellations, which was not typically the case with the sort of more legacy and expensive high-resolution platforms. This slide here is actually from a presentation by TerraWatch Space. He's basically done a summary of the state of the industry in 2022, and on the left-hand side, in the orange box, that's all the companies that are providing imagery. And as you move across to the right, we go more to companies that are integrating information or building services on top of that. So the far right box under weather and climate risk, this is companies that are using data and transforming it into insights, essentially. So getting quite far away from the pixels, but actually focusing on the meaning of the data. So to get on to what are the uses of AI specifically and satellite imagery, and just to recap what my interpretation of AI means. AI means a particular branch of machine learning characterized by training very deep models with millions or even billions of parameters. So that's what I classify as AI. In terms of applying to satellite imagery and with the social good dimension, I've identified several key areas here. The first of which is disaster management and response. And then related to that is the reducing the risks associated with disasters, and then also monitoring different kinds of disasters, both over short time frames and longer time frames. Continuing with the theme of monitoring, there are other applications around deforestation. For example, lots of companies are monitoring the Amazon, and also more generally wildlife conservation. Moving, I guess, away from sort of disaster and wildlife to the sort of urban situation. There's lots of work being done to monitor urban growth and understand how urban areas are being used and the resources that they consume are being impacted. So we have both urban planning and water resource management. Finally, there's an awful lot of work that takes place around crop yield and understanding agriculture. In particular, there's a lot of interest in precision agriculture, which I won't talk about too much, but obviously the impacts on social good would be that you can improve production of food. So the way I've structured my presentation is basically a series of short case studies that will highlight some of these areas. The first one I would like to draw your attention to is the use of machine learning and aerial imagery for disaster response, in particular the recent earthquake in Syria and Turkey. This disaster was characterized in one sense by being over a massive geographical area, and satellites were the first platforms to be able to image the entire area. There was devastation of a very large area, lots of properties collapsed, and the traditional way of understanding and mapping the impact of this disaster would be humans processing all of this imagery and annotating where they can see that buildings have been damaged. The problem with that approach is it's obviously relatively time consuming. The more imagery, the larger the area, the more man hours that's required to process it. And you can't go from from nothing to a big sort of analysis task force quickly. This is where machine learning comes in. So the project I'm highlighting here is a recent project. It was a collaboration actually between Microsoft. They have an AI for Good function, the Defense Innovation Unit, and Berkeley AI Research. And what they did is they basically trained and fine-tuned models to detect destroyed buildings in the imagery captured over the Turkey earthquake area. And it was quite impressive what they achieved. I think within about a week of the disaster, they were able to fine-tune and apply a deep learning model to identify all of the damaged buildings over a very large area. They processed imagery captured over 4 key cities and were able to identify which of those cities had sustained the most damage, and also quantify both the number of damaged buildings and also estimate the number of people impacted by the loss of their property. And you can just see on the right, these images we have on the left here. This is the captured imagery, which is very high resolution imagery, which is possibly required for improving the accuracy of the model. It's 30 centimeter imagery. And on the right, those green and red markings. The green are areas that have not been damaged, and the red is areas that have been damaged. So this is the output of the machine learning model that's trained to detect the damaged buildings. And this information, as I mentioned, was produced very quickly and applied over a very large area. This particular case study is in my newsletter number 11, if you want to read more details about it. The second example is around mapping disaster risks. And so this is obviously assessing the risk to an area before a disaster has occurred. And satellite imagery has been used for a long time to understand risk factors, particular disasters that we would care about in this context would be earthquakes and hurricanes. And in this particular piece of work, machine learning models are trained to identify the material of the roof, because the material of the roof tells you a lot about the structure of the building and how impacted it could be by a disaster. And this was a recent competition, I think 1 or 2 years ago, using drone imagery in this case. So again, the similar idea here, that just by training models to detect particular features in imagery, you can start to understand the risk to an area. Moving on to, I guess, a real-time application. This slide is presenting some work actually published by Google on their blog relatively recently. And basically, what they want to do is to be able to show on their maps in real time the location of wildfires, because obviously this information would be useful for first responders and probably quite vital if you're also directing traffic in a disaster, which Google Maps would be doing potentially. So what they did is they actually were able to combine data from a variety of satellites, not just one, but actually multiple satellites. And by fusing that data together, they were able to actually get better accuracy, essentially, in detecting the location of fires and the boundaries of fires. And because of the sort of constellation of satellites that exists, they're actually able to do quite real-time monitoring. And the system they developed was actually able to identify the location of wildfires and produce alerts on a timescale of every 10 to 15 minutes. This is only really possible by using the machine learning to actually fuse these multiple sources of imagery, and also to train a model that's got the right required level of accuracy and specificity to detect the fire in the first place. And obviously, because it's a machine learning based system, it can be essentially fully automated and run in real time. And all of this adds up when you're talking about responding to events like fires, which can change very rapidly. So that was a very interesting.
Can I ask you a question? Is there a common? I assume there's a common format, or like a mode of data exchange between the satellite, to reconcile the images, to map them. Is there like a common format that they all use, or how does it work?
It really depends. There is a sort of imagery format called a GeoTIFF, which is basically just an image, a TIFF image with metadata attached to it that locates the pixels on the Earth. You can get some challenges if you're trying to mix modalities of images. So if you try to combine optical with radar, for example, then the file formats might require slightly different handling. In general, all of the models are just trained on arrays of numbers, so you at some point need to transform them into this common format. But that's, I guess, part of the beauty of machine learning, is that once you have the data in the right format, the model itself doesn't really care too much about where that data was acquired. So there definitely is some challenges to working with remote sensing data around some of the specifics of the data formats, but in general, once you've overcome those sort of pre-processing tasks, then you can just proceed with a very pretty standard approach to training machine learning models on that data.
Yeah, because I assume that with different sources, right? So we have different satellites, could be from different countries or different orbits, right? Or different type. Or some satellites have been launched like many years ago. Some have been launched this year or last year. So technology might change, and maybe the product, the images they produce might be a bit different.
I think a useful point to raise there, that it's only really been in the last 5 or 10 years that it's actually been able to build systems that like aggregate data from lots of different providers, because traditionally each provider would have had their own way of distributing data, and they didn't really have a standard format for accessing it, and that's actually changed quite recently. Now there is a more standard way for sort of querying and accessing data from different providers. And there are actually several companies, and their business model is to provide a single point of contact for all the data across all of these different providers and sort of standardized APIs, essentially. So building services has gotten, I think, a lot easier than it would have been 5 or 10 years ago.
Yeah, especially on the amount of data is huge, right? So you have so for the researcher to have an easy access to API and so on is a great plus. Thank you.
Yeah, when you're talking about data that can cover the entire Earth, you're talking about petabytes of data typically. And it's only again relatively recently there's been platforms which can sort of work with that amount and that volume of data. So an example would be Google Earth Engine or Microsoft Planetary Computer. And yeah, it generally does require some kind of special tooling once you start talking about really large images and lots of data essentially.
And in the previous slides, when you showed the earthquake pictures, so what frequency, like what is the revolution, like how often they would go on over that area? I assume that they have to be once a day or twice a day, or it depends.
Yeah, it really depends. So there's as I mentioned on the first slide, there's now many companies providing imagery. This is the left box over here. And some of them will have constellations that might be just 1 or 2 satellites, and others will have literally hundreds. Something like this image here from Maxar, I think that's a Maxar image. I think in their constellation they only have a handful of satellites, and so you might be waiting longer to get an opportunity to image an area. Whereas a company like Planet, they have, I think, hundreds of satellites in their constellations, and they can capture an image every couple of hours.
I think they provide pictures for Ukraine, or the Russian tanks or something of the company in particular.
Yeah, typically if you see those examples on BBC News or whichever website you look at, and it shows a high resolution imagery, that will be probably Maxar or Airbus. They have I guess the Rolls-Royce of satellite platforms. But yeah, there's a bit of a trade-off there because they're also probably the most expensive imagery, right? And there's obviously a bit of a trade-off, of resolution versus cost for aerial and satellite images. And just because you can get a satellite over a location doesn't mean you're going to get a good image, because very often clouds will, spoil an image. So you might have to take several passes to actually get a cloud-free image. There are other ways of imaging, for example, using synthetic aperture radar, which can penetrate clouds. So there is innovation in the market to address that challenge as well. Cool. Thank you for that question. The next use case is landslide detection, and actually this is using synthetic aperture radar imagery. And the goal here is to have an alert system so that a government or an organization can be notified, I guess, very quickly or almost in real time if a landslide has occurred. And this is what you would call a change detection problem. So you have images before and after at a location, and you basically train a model to detect if there's been a significant change, and if there has, to identify that change. And then you can train models to look for specific kinds of change. So that's what's been done in this case. And they basically take these images at different times and identify, okay, there's been a change, and we're going to predict the probability that change is due to a landslide rather than just, some change in the area due to, I don't know, people harvesting or whatever. So again, that's an application which is only really possible, or at least only possible to automate, by using machine learning. And as I mentioned, one of the benefits of using this kind of imagery, synthetic aperture radar or SAR imagery, is that you can use it at any time and it will penetrate the clouds. But one of the challenges of that data is that there are lots of funny artifacts in it that are not intuitive for humans to look at. So it's actually, because you can train a machine learning model to become, I guess, insensitive to some of those artifacts and only focus on the meaningful change in an image, that you can get a really accurate system. So that was another recent innovation. So this is an interesting area. I'm particularly attracted to the idea of improving weather forecasting. So the challenge here is, how do you get accurate weather forecasts, or in this case, specific case, rainfall forecasts, in locations where you do not have highly accurate radar data? What you do have in nearly all areas of the world is low resolution data from geostationary platforms. But what you really want is to be able to enhance the insight you can get from that imagery. And that's what has been done in this case using machine learning. So what they've done is train a particular kind of model that can fuse, again, data from, I think it's a time series in this case, and do it in an intelligent way. So if you image the same location but multiple different times, you can actually extract greater insights into the information spatially than if you just have a single image. And that's what's been done in this case. They were able to combine a sequence of images and generate a more accurate spatial representation of rainfall. And in this case, they were able to generate, I think, enhance both the spatial and the temporal resolution of predictions and create a very accurate rainfall prediction service using machine learning. So I think that's quite an interesting example of, again, how machine learning can generate capabilities that are not possible for a human because of its ability to learn from deeper data. This one was in the 6th newsletter that I published. Okay, flood detection. This is, again, generally treated as, it could be treated as either a change detection task or a task where you're trying to detect the presence of flood in a single image. And this particular example was quite interesting because they were training models to do several things. The first one was to identify the location of flood water, and then also to identify flooded roads and buildings in flooded areas, and then also to estimate, given the flood that's occurred, the fastest way to drive through the flooded region. So that's quite an interesting machine learning proposition, because there you're not just extracting information about the pixels, but you're also trying to understand the implications for people traversing infrastructure inside that image. And obviously being able to identify the quickest way through a flooded region will be invaluable to first responders trying to reach people in distress. And I think, again, this shows that machine learning is very capable and can provide sort of additional information beyond sort of basic prediction.
Even
so that was really interesting.
Even today, I mean, even if we don't, it would be even very useful for Google Map or Apple Map or Waze or this kind of apps, right? And it has happened to me, that sometimes in a storm, some trees will block a road, right? But then the system will tell you, okay, you have to go through that road, but you cannot, right? Because it doesn't know that has happened, and you have to circle around without a GPS. So it's a bit sometimes not easy to do if you're not familiar with the area. So even today, I think for the beyond disaster, it would be very useful.
Oh, absolutely. I can imagine, in a disaster situation, even saving a couple of minutes might have a very significant impact on the people that are being rescued. And I think that's where obviously these services want to get to, where they can update information in real time and make the most accurate and timely predictions. So I think we'll get there. It's quite an exciting time for that sort of service development. Moving on to biomass. So obviously, well, not necessarily obviously, but we basically have a need to understand where carbon is being trapped in the natural world. And in particular, we need to be able to measure what's called the biomass. So this is literally the mass of biological matter, generally both above and below ground, but specifically above ground. People basically want to measure how many trees there are and how dense they are and how large they are, because this tells you how much carbon they're storing. And typically, historically, this was done in quite a destructive process where you literally go and chop down trees and weigh them to understand, in an area how much tree mass there is. But actually, people are now training machine learning models to do this. And what they do is they basically train a particular kind of machine learning model that, given, say, the images on the bottom, they can actually predict very accurately the amount of mass of trees in that area. And this is important because it's refining our understanding of how much biomass is available, and that is helping us to inform our strategies around dealing with carbon emissions. So that's a very exciting
that picture on the left, Robin? So what is dark? Are the trees, or the biomass? This is the gray.
So one is the left-hand one, which is called expected. That's the true image, and then that's the model. Expected to be what the model is predicting to be trees and not trees, and then on the right is the actual truth. Because typically the way you train these models is somebody has to go and label all of the pixels in the image which are actually trees or
The,
not
the, the
trees,
trees
and
are
train
the
them.
black area, the dark area. So the gray.
Yeah, that looks like it. I'm not actually dug too deep into that, but I'm assuming that's pockets of trees surrounded by grass, for example. Yeah,
Really
and
useful
really the name of the game here.
It's very useful for Canada, especially, right? Because they have massive areas that nobody lives there. So it's not surprising.
Yeah, I
Canadians
mean,
are very good at satellite imaging, right? Because they have a lot of land mass to survey and to monitor, and a very small population.
yeah, and you don't necessarily need to know just where the trees are, but you might also want to know their health, right? So you might want to identify if there's been some disease outbreak in an area, and you can only really do that kind of mass area sort of surveying in an automated approach. So we definitely need machine learning to do that for us.
We'll take question at the end, Michael. I see the result somewhere. Thank you. Go ahead.
Getting close now. Wetland monitoring. So wetlands are a specific kind of environment that are critical for, I guess, both wildlife and animal life. Again, machine learning is used not just to identify wetland areas, but can actually also be used to generate what's called synthetic data. Because one of the challenges you often have in machine learning is that you just don't have enough data, or you might have a good amount of data, but there might be some edge cases where you don't have an awful lot of data, and this is generally a problem. So what's been done in this particular example is to use one machine learning model to generate basically fake or synthetic data, which can then be used to tune to train a model which is seeing some synthetic data but also some real data. And what was demonstrated was actually you can get a more accurate model by combining the data set, which is the real and the synthetic, than if you just use the real data. So this is really quite exciting because it shows us it's a realistic technique which can generate useful training data and improve the accuracy of models. So that was particularly exciting for me anyway. Models generating training data to improve models. Yeah, in this case they were using GANs, I think, yeah. But you're probably aware of there's an awful lot of buzz in the media at the moment about generative models, which can create images and all kinds of other data. And the uses for that is beyond just entertainment. Actually, can be used for practical purposes. In this case, training machine learning models. I think in this case there was specific kind of wetlands which are not very well represented in the training data set, and they identified that and generated more examples that would look realistic, but were actually completely synthetic, and that was able to improve the model performance. So I think that's a really exciting direction for research. And that was in newsletter number 5. So I need to keep moving this Zoom bar around so I can read this slide. Harmful algae bloom detection. So, okay, algae blooms, these are caused, I think there's a number of factors which give rise to algae blooms, including temperatures and also nutrients that have been the rain has come and taken nutrients from fields and put them into water, and then when that reaches the sea you get these algae blooms which can be toxic to both humans and also the marine life. Again, there's a requirement really to detect these as soon as they occur for first responders, and just even having an insight to the scale of the problem. And typically this is done I guess by people reporting it, but machine learning again can be used with basically by looking at the spectral information in an image to identify very specifically when these blooms have occurred. And this image was from a recent competition that was run to detect these. And again, the name of the game is achieving high accuracy and real-time results. So that's been quite
It's
nice.
A big deal. I mean, it's happening right now in Florida. I think it's in Florida.
Oh, is it?
Algae bloom are coming. Yeah, it's.
Yeah, looks like a.
I don't know if they use satellite imaging, maybe to monitor.
Yeah. Okay, and this is the final one actually. This building coverage assessment. So this is getting away from like disasters, and this is more generally needed to understand the urban fabric. So typically we're used in the West, to having accurate maps of areas, but in many parts of the world they do not have accurate maps, and you cannot even necessarily know, the size of an urban area or identify changes to it. You could, for example, use very high resolution imagery like we showed for the disaster response, but that's typically quite expensive and maybe cost prohibitive for large scale monitoring and, frequent, maybe annual remapping. So actually what was demonstrated in this particular piece of work was that you could use lower resolution, actually even free imagery provided by the Sentinel program, and generate accurate estimations of building density in urban areas. And again, this is possible because of machine learning, which can basically do better than humans at identifying features which are reliably representative of buildings in relatively low resolution imagery. If you look at this image on the right, the colored patch over here is actually the image as captured by the Sentinel satellite, and on the right, in the black and the yellow, that's the predictions from the model. And they were actually able to show that by using machine learning, they were able to generate very accurate estimations of building density in some of these areas.
How do you get the
so
ground
that's
truth?
really
How do you
exciting.
get the how do you get the ground truth? Like because you train the model, you probably have this. So you have these fuzzy satellite images, but you need the real target, no?
Yeah. For that, I guess you could either, I'm assuming somebody would have annotated higher resolution imagery over a smaller area and then provide that as truth. And then you train
Maybe
a model over.
larger city, a larger urban area, and then extrapolate for the rest.
Yeah, that's it. Typically, you'd want to get in your data set data representative of where you want to apply the model. So it's typically a requirement that you would annotate some data before training a model and checking how it performs in that area. And this is actually a really good point because we've got lots of data sets for like North America and Europe and, but many parts of the world, there are not data sets available. And that's something that definitely needs to change.
And that's a good point. Yeah, you can train data on, other data from other continents and then apply it to Africa or some other countries. I've seen also interesting application of this type to monitor like building destruction, like in areas in Ethiopia, so on, you have like civil war. So they want to monitor, like damages to villages, cities, and so on. So they do like, you can look at the buildings. So it's a bit like what you showed before, like being destroyed by, earthquake and so on. So they look at the urban monitoring to look at the development of like, civil warfare in the area, and then also to track refugees. So you see that, the buildings have been destroyed, and you expect refugees to leave that area and to move elsewhere.
Yeah, I mean, I expect that's a longer term goal. We'll get to the point where this imagery can be used to basically map the entire Earth in real time and identify all the structures and all the different kinds of like human activity. Okay, so moving on to more the ethical side. So what are some of the challenges, the key challenges around using AI and satellite imagery? First of all, I think there are ethical considerations. So obviously satellites can look wherever they want essentially, and the data that's captured on them could be misused or used to mislead people with unintended consequences. And I think what's really required there is guidelines to ensure that this data is used in a transparent manner and that people are held accountable for the way it's used. Data privacy is a big challenge. So how do we protect the rights of individuals to have privacy when there's continual monitoring from overhead? Again, I think safeguards are required there. And how do we ensure fair access to data? Many of the sort of high resolution data platforms are only accessible if you have very deep pockets. And as I mentioned before, there's a bit of a bias in what's possible because of the fact that data is only being purchased over certain parts of the world. I mean, that's something we need to address. And how do we make data more widely accessible? For example, like you can't even train a data on some parts of the world because there's no annotated data sets available. That's definitely an important point. Some of the trends and opportunities. I didn't miss something there, didn't I? As I mentioned, we're seeing greater and greater use of machine learning and AI in particular. And what this is enabling is processing of data at scale and very rapidly. It's also basically reducing the cost of processing data because, it had to be performed manually in the past. That would have been more expensive. And we're seeing that we can achieve faster and faster responses to this data. There's definitely a growth in demand for this data, as demonstrated on the first slide. We showed all the companies that are now consuming that data and performing analytics on it. And I think what we're going to see is that the trend is to larger and larger data sets, both labeled and unlabeled. There's been many advances in the actual satellite imaging technology. As I mentioned before, we've now got synthetic aperture radar. There's also other modalities of imagery that are going to be captured soon, hyperspectral, multispectral, different parts of the optical spectrum as well. There's also an increasing amount of processing happening on board the satellites. Historically, it was relatively limited, and you would just downlink your data to the Earth and do processing there. But you can actually enable different kinds of workflow if you do the processing on the satellite. So if you imagine something like fire detection, you can enable potentially a faster response to that information if you do the processing on the satellite. I think in future there's also going to be greater networking in space, so you won't necessarily have to wait a relatively long time until your satellite comes over a downlink opportunity. You'll be able to downlink going via other satellites. In general, another trend is an increasing amount of collaboration between companies and the private sphere and governments. It used to be just governments that would own Earth observation satellites, for example, and then we're seeing greater and greater numbers of companies that own those that hardware, and there's also been a trend towards collaboration. The government preferring to buy data from private companies rather than launch their own satellites. So that concludes my presentation, and I now open the floor to some questions.